Okay, so this explains what we're going to be doing, or why we're going to be doing this when we have an integral with infinity as one of our limits of integration. That causes two problems, which you can check up there. But what today's lesson is going to show us is that we can replace infinity with a variable, and then we can let that variable approach infinity and take the limit. So that's kind of a tricky way to get around that problem. So we'll look down here and converge. When things converge, that means they come to a head, they come to a point. So if it comes to a value and it diverges, the Robert Frost poem, two roads diverged in a yellow wood, and I looked down one as far as I could to where it bent in the undergrowth, then took the other as just as fair, though as for that the passing there had warned them really about the same. Blah, 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 and that has made all the difference. I took the one less traveled by, and that has made all the difference. All right, anyway, sorry for that English diversion. Anyway, back to our lesson here. So pretty simply, we're just going to take the limit as b approaches infinity of the integral from 2 to b, and maybe do a little rewrite on that, x minus 2 to the negative 2, like so. Now, if we integrate that, we can add 1 to the... Now, you got to be careful with what you have inside there. Luckily, the derivative, like we don't need a u substitution. This has come up in some of our previous notes because du is equal to dx. So we're just fine here. We can just add 1 to the exponent. So that would be negative 1, and divide by the new exponent. That would be negative. So we're going to have negative 1 over x minus 1, and that's going to be from 2 to b, and we're still taking the limit of that as b approaches infinity. Okay, so if we plug b in there, we're going to have 1, negative 1, b minus 1, and then we have minus, and then we have this negative, so that's going to be plus, or I can show that a little bit better. It's going to be minus a negative 1 over, and if we plug in 2, it would be 2 minus 1. And we are still taking the limit as b approaches infinity. So that's going to give us negative 1 over infinity minus 1 is infinity plus 1. Okay, and negative 1 over infinity is going to be basically 0, so 0 plus 1, so that equals 1. Alright, and it already says that's an example that converges, so we don't really need to worry about that. Okay, but the fact that it does go to a number means it converges. Alright, so we're going to just try and do the same thing again here. So we have the limit as b approaches infinity, 2 to b. Now here, I don't want to rewrite that because the integral of that is the natural log. So I'm not trying to write that to the negative 1 power. We never integrate x to the negative 1 power trying to use a power rule or anything like that. We need to know that 1 over u is the integral of 1 over u is the natural log. So we need to be careful there. Alright, so let's go ahead and integrate that. And like we just said, that's going to be the natural log, x minus 1 from 2 to b. So one more step there, writing that limit down over and over again. The natural log of b minus 1 minus the natural log of 2. Okay, so 2 minus 1. So that's going to be the natural log. Infinity minus 1 is infinity, so the natural log of infinity, I don't really need the absolute value there anymore. And then the natural log of 1 is 0. E to what power equals 1? E to the 0 power equals 1. So the natural log of infinity is infinity. So the limit does not exist, so this diverges. It doesn't go to a specific value. All right. So those are the two main things that'll happen. So we can try it again here. So this is going to be the limit as b approaches infinity. So this is the same process. We're just doing the same thing over and over again. From 0 to b of cosine x dx. All right. So that's going to be the integral of that is sine. So that's sine x from 0 to b. So that's going to be the limit as b approaches infinity of sine of b minus the sine of 0. So the sine of 0 is just going to be 0. So this is going to give us the sine of infinity. And if we keep going out towards infinity, that's going to oscillate. So that does not exist, so that diverges also. Okay. So a little change here. This time, all right, so slight variation on this one. We've got the negative infinity down here instead, but it's going to be the same idea. So we're going to take the limit as b approaches negative infinity from b to 1 of e to the x dx. So limit as b approaches negative infinity. If we integrate e to the x, we get e to the x, and from b to 1. So that is, one more time, the limit as b approaches negative infinity of e minus e to the b. Okay, so that's going to be e and e to the negative infinity, which is going to be 1 over e to the infinity, which is going to be infinity, 1 over infinity. Okay, which is 0. I don't know if I needed that many steps or not. Seems a little bit whatever. Okay, now what's going on here? Alright, so I was looking at this and it says using L'Hopital's rule, but also we're going to need to integrate by parts. So we're going to do a couple things here. First of all, same time, we're going to take the limit as b approaches infinity of the integral here. But I'm going to wait to write the integral because I want to do the integration by parts and get my ultraviolet voodoo first. So colors, what colors did I use? Purple and red. Alright, so we're going to let u be x, and then so take du, that's going to be dx. And then if we let e to the negative x be v, and then we want to integrate that, that's going to be the derivative of e to the u is e to the u, so that would be this. But if we took the derivative of that, we also have to multiply by du, which would be -1, which means that would be negative. So to deal with that, we need this to be negative. Okay, so remember we go this way, ultraviolet, that's u and du, that's v and dv, or dv and b going backwards. We take derivatives here, we integrate here. So that's a nice little review. So that's going to be negative x e to the negative x. That's the ultraviolet part. And then we have the integral part, which will be this, which is normally plus. This will be minus. And then we'll just have, or no, it's minus here, and then this will be minus. I'm going to write that in separately. And then here we're switching this to 1 and b. And then that's just e to the negative x dx. Alright. So, I think we're okay there. Let's do this. Have that. This will come out, but then when we integrate that, we're going to get a negative again. So those two are positive, but when we integrate that, we get a negative. And then I'm going to write that as 1 over e to the x. Alright. And that's going to be from 1 to b. So then if we plug that in here, we're going to have negative b over e to the b minus 1 over e to the b minus, plug a 1 in there, we're going to get negative 1 over e minus 1 over e. Okay, so these have a common denominator, so we could do this, and then that's going to be plus 2 over e. And we have our limit down here as b approaches infinity. So if we try to do that, we would get negative infinity over infinity, and that's where the L'Hopital's rule comes in. So in trying to do that, that's not going to work for us. So we want to take the limit as b approaches infinity, and we want to take the derivative of both of those. So the derivative of the numerator is negative 1. I should have left a little space there, but and the derivative of that is itself. So remember, when you do L'Hopital's rule, you absolutely have to show the limit of the derivatives. You have to write limit, and you have to have the derivatives of those things. Now this we could have separated on the side, so we're not taking the derivative of this. That's a constant. So we have 2 over e on the side over there. Maybe put this in parentheses to emphasize that. So now if we let that go to infinity, we're going to have negative 1 over e to the infinity plus 2 over e. And so then that is 0. And so our answer is 2 over e. Alright. So I don't know, I kind of like that. It had a review of integration by parts. It had a review of L'Hopital's rule, so I like that question. Alright, so let's wrap this up. Last one. So you can see these notes mostly tend to be a little bit shorter than our AB notes because I try to cut them up into parts a little bit more. Some of the problems are longer. So, alright. So now our last example here is if we have infinity on both. So the first thing we should do, I guess, is separate that. So we're going to go negative infinity. I'm going to go to 0. And it's going to be 1 plus x squared dx. And then we're going to add the other part, which would be 0 to infinity. Alright. So we want to take the limit. I'm going to do 2 steps at the same time. So I'm going to take the limit as b approaches negative infinity. but I don't want to write this out again. So I'm just going to go ahead and integrate it now and plug in and put the b in. So what I would be doing next normally is I'd write this exact same thing down, except I would put a b right there for this part. Okay. So, but I'm going to integrate that. That's arctangent, inverse tangent. We've had that a couple times, so hopefully you're starting to recognize that one from having seen it a few times. And then that's going to be b to 0. Then over here, we need a different one because it's going, so we're going to say c approaches positive infinity. So this is going to be 0 to c, and that's going to be the same. It's a little awkward there. I started to write an x. Inverse tangent. And this one's from 0 to, oops, that's funny. That's the step I was trying to skip. So how about that instead? Yeah, it's better. Okay, so this is going to be the limit b approaches negative infinity. That's going to be the inverse tangent of 0 minus the inverse tangent of b. 0, 0 for tangent, so that's 0. And then this is going to be if we substitute that in, that would be negative infinity. All right. And now over here, that's going to be limit as c approaches infinity of the inverse tangent of c minus the inverse tangent of 0, which we just talked about as 0. So this is the inverse tangent of positive infinity. Okay. All right, so I quickly did a graph of tangent for you so we could think about these two values here. So the inverse tangent of negative infinity, so when does tangent equal negative infinity at pi over 2? Well, remember, we're doing the limit as b approaches negative infinity. So as this approaches negative infinity, this approaches negative pi over 2. So that's going to be negative pi over 2. And then over here, as that approaches infinity, tangent is going to approach pi over 2. So that's going to be pi over 2. So pi over 2 plus pi over 2 is pi. All right. So there we go. It's about that time. Have a good day.